The S-linked list class will be our generic singly linked list class. It's going to implement the S-list interface. Because it's a linked structure, it will use the same generic node class that's used in the linked stack and linked queue classes that we saw earlier in the course. We're going to make a change to the node class in that we're going to make it package private. The reason we're going to do this is because we want to leave open the possibility that we create a utility class that operates on linked lists. Now, if we want a utility class that operates on linked lists, it probably needs access to the nodes of the linked list, so it needs access to the node class. If we make the node class package private, then we can define the utility class in the same package as S-linked list, and the utility class will still have access to the node class inside of the linked list class. We're also going to have some package private methods that return the head and tail nodes of the list, and a method that returns the node given an index. And again, this is so that the utility class can have access to the nodes of the linked list. So here's the start of our S-linked list class. We've got our static inner class called node. Notice that there's no access modifier here, which makes it package private. The implementation of the node class is exactly the same as the node class in the linked queue and linked stack classes. We're going to have a field that represents the number of elements in the linked list, so that's the size of the linked list. We'll have a private field that represents the head node of the list, and we'll have a private field that represents the tail node of the list. Notice that both the head and the tail will be null if the list is empty. So if there are no elements in the list, then there is no head node or tail node. We've got a package private method that returns the head node, and we have a package private method that returns the tail node. Again, this is so that a utility class can get access to the head and tail nodes of the linked list. The linked list constructor that has no arguments simply creates an empty linked list. So we set the size to 0, and in an empty linked list, there is no head or tail node. So we set those fields to null. The number of elements in the list is easy. We just return the size of the list. If we want to add an element to the end of the list, then that's identical to enqueuing a new element. That's identical to enqueuing an element onto a queue. Adding to the end of the list, normally you only adjust the tail node. So for example, if we want to add an element to the end of this list of size 3, then we make a new node called n. We then take the tail node and link its next pointer or its next field so that it points at the new node n. Then we adjust the value of tail so that it refers to the newly added node. When you add to the end of an empty list, that turns out to be a special case. So if you add a node to the empty list, then both the head node and the tail node now refer to the new node that's been added to the list. So when you add to the end of an empty list, you end up having to adjust both the head and tail fields. So that's going to be a special case in our add method. Here's the implementation of the add method. The first thing we do is we make a new node n to store the element. Here's the special case for when the list is empty. When the list is empty, we make the head node refer to the new node n. If the list is not empty, then we join the new node n to the tail node, and we do that by writing this.tail.next is equal to n. In either case, we then have to adjust the tail node so that it points to the new node n, and then we have to increase the size of the list by 1 because we just added a new element to the list. Many of the list methods operate by using an index. So when we perform an operation that uses an index, we have to move to the node that's at or near the given index. The reason we have to do this is because we only have a reference to the head node in the linked list class. So if we want to move to the middle of the list, then we have to follow all of the nodes until we get to the node that we want. Because most of the methods in the linked list class operate using an index, then it becomes useful to write methods that will validate an index and that move to a node at a specified index. A valid index for a list is an index that is greater than or equal to 0 and strictly less than the size of the list. Our validation method simply takes in an index and checks if the index is negative or if the index is greater than or equal to the size of the list. If it is, it simply throws an index out of bounds exception. Otherwise, nothing happens. The move_to method moves to the node at the given index. The move_to method assumes that the index is valid for the list, and that's to avoid revalidating the index. So the assumption here is that some other method in the class is going to call move_to, right? So move_to is not a method that will normally be called by some other programmer. So we can assume that the other method that's calling move_to has already validated the index. So we're not going to revalidate the index in move_to. The first thing we do is we check if the index is equal to the size of the list minus 1. And if it is, that's just the tail node. So we're going to return the tail node. And that's to prevent having to move through the entire list to get to that node. We already have a reference to it, so we might as well just return the reference. Otherwise, we're going to start at the head node, and we're just going to follow that many links to get to the node that we want. So we just write a little loop starting at 0, goes up to but not including the index, and we just set n to n.next each time in the loop. When the loop finishes, the reference n will be pointing at the node that we want. Alternatively, you can implement this using recursion. So again, check if the index is equal to the size minus 1, and if it is, just return the tail node. Otherwise, call the recursive method, where the recursive method takes in a node that's the head of a list, and an index that is the index to move to relative to the head node. So our private method takes in a node n, which is assumed to be the head of a list, right? And index is relative to that node n. So if index is 0, we want to return the node n. If index is 1, we want to return n next, and so on and so on and so forth. The method's recursive, so our base case is simply if the index is 0, then we are already at the node that we want, so we just return n. Otherwise, we move to the node at index minus 1 of the list that's one smaller than the current list, right? So we move to the next node, and then decrease the index by 1, and and then call move_to recursively. So given the move_to method, the methods like get and set are trivial to implement. Now, if you look at the complexity of move_to, you should realize that move_to has complexity in big O of n, because it has to follow up to n minus 2 links in the worst case. And that means get and set are also going to be in big O of n. The get method is easy to implement once you have move_to. You simply validate the index, then you move to the node at the given index, and thus return the element that's in the node. Set's very similar. You're going to validate the index, move to the index using the move to the node at the given index by using the move_to method. And then set should change the element that's in the node, but it should also return the element that's currently in the node. So we're going to remember what the current element is. We're going to change the element so that it refers to the new element, and then we're going to return the old element. To insert an element at the front of the list, that's identical to pushing an element onto the top of a node-based stack. Now this has complexity big O of 1 for a linked list. And you should compare that to what happens in an array-based list, where inserting an element at the front of the list has complexity big O of n. Right? Now, the reason that the complexity is big O of n in an array-based list is that we have to move all the elements of the list one position to the right in order to make room for the inserted element. Whereas in a linked list implementation, we just make a new node and join that to the front of the list. And so that has complexity big O of 1. So inserting at the front of the list, we just make a new node. We're going to call that toAdd. We're going to set toAdd's next link to point to the head node. And then we're going to adjust the head node so that it points to the newly added node. So add front, we simply make the new node, right? It stores the element. We adjust the next link of the node so that it points at the current head node. We then adjust the head node so that it points at the new node, and then we increase the size of the list by 1 because we just added a new element to the list. If we want to insert into the middle of the list somewhere using an index, then that requires adjusting the next link of the node that's at index I minus 1. So in other words, if I want to insert an element at index 2, I want to insert an element here, I have to adjust the next link of the node that's in front of the node at index 2. So after inserting the 4, the list looks like this. Right? And notice that the link that needs adjusting actually belongs to the node at index I minus 1. So to insert into the list using an index, we first move to the node located at index minus 1. And we're going to call that node n. We're going to create a new node for the element that's being inserted, and we're going to call that toAdd. We want to get a reference to the node that's after n. Right? So we follow n next. We're going to call that node after. We want to do that because we want to join the node toAdd to the node after. Right? So that node becomes the node after the inserted node. We then want to take n and adjust its next link so that it points to the new node. We take the new node and adjust its next link so that it points to the node after. And that produces the following list. So the implementation of our add method looks as follows. If the index is equal to the size of the list, then that means that we want to add the element to the end of the list. We already have a method that does that. It's just called add. So we'll call the add method and add the element to the list and then return. If the index is not equal to the size of the list, then we need to validate the index. So the index has to be between 0 and the size minus 1. If the index is 0, then we're adding to the front of the list, and we already have a method that does that, so we'll just call the add front method. Otherwise, we're going to move to the node that's in front of the index. We're going to create our new node called toAdd. We're going to store the element in it, and we're going to set its next link so that it points at n next. So in the pictures, we did these all in separate steps. Right? We made a node after that points in the node after n, and then we joined n to toAdd, and then we joined toAdd to after. In the implementation that I'm showing you on the slides, we're going to make the new node toAdd, and we're going to join its next node directly to n next, which is just after. So we can do all of those steps in one line like that. Finally, we're going to adjust n next so that it points to toAdd, and then we're going to increase the size of the list by 1. To remove the front element of the list, That's identical to dequeuing an element from a node-based queue. And now remember, when we dequeue an element in a node-based queue, that has complexity O1, because all we have to do is unhook the first node from the list. Whereas if you have an array-based list, then removing the first element from the list is in big O of n. And that's because we have to shuffle all of the remaining elements in the list one position to the left. To remove the front element of a list, you first obtain a reference to the node to be removed. So we're going to call the current head node to remove. We're then going to update the head node so that the head node now points to the second element or the second node in the list. We're going to decrease the size of the list by 1 and return the element that's sitting in to remove. Our remove front method looks as follows. We check if the size of the list is 0 or if the list is empty. And if it is, we can't remove any element, so we throw an exception. Otherwise, we create the node to remove, which just refers to the head node. We're going to adjust the head node, so the head node now refers to remove next. There's a special case when we remove a node or an element from a list of size 1. So when we remove an element from the list of size 1, the resulting list is empty. That means we have to adjust the tail node. So we have to make the tail node point or refer to nothing. So we set the tail node to null. Normally, you don't have to adjust the tail node when you remove the element from at the front of the list. But if the list only has one element in it, then you also have to adjust the tail node. Then we decrease the size of the list by 1 and return the element that's in the node to remove. Removing an element by index is similar to inserting an element at an index. You end up having to adjust the link belonging to the node in front of the node that you remove. So you want to move to the node at index -1 and then remove the node that's after that node. So to remove the third element from the list, I want to move to the second node in the list and adjust that next link. So first we move to the node at index I-1 and call that n. I'm going to make a variable called toRemove, and that refers to the node that we're removing. We can get toRemove as n.next. I'm then going to create a variable called after that refers to the node after the removed element. Right, so after is going to be that node there. The reason I want this node is because I want to join n to after when I remove that blue node there. So we're going to unlink the next link of toRemove. So in other words, we're going to set toRemove next to null. And then I'm going to link n so that it refers to after. So n next now equals after. And then we can decrease the size of the list by 1 and return the removed element. So here's the implementation of the remove method. If the index is 0, then we can simply call remove front. If the index is not 0, we're going to validate the index to make sure that the index is valid. Then we're going to move to the node that's in front of the one that we want to remove. And then we're going to call this remove after method. So the remove after method is the method that actually removes the node that's immediately after the node n. The reason we want to do this is because when we implement the iterator, it's very useful to have a remove after method. Remove after simply implements the steps that are shown in the slides. So the node that we want to remove is just n.next. The node after the one that we want to remove is just toRemove.next. We're going to unhook toRemove from after by setting its next link to null. We're then going to make the node n, we're going to link it to after, so n next equals after. Again, there's a special case where if you remove the last element of the list, so if you remove the last element of the list, then you have to adjust the tail node because the tail node has been removed from the list. So if after is null, that's one way, that's how we're going to detect if the last node was if the last element was removed. Then we're going to make the tail refer to the node n, right? Because n is the node in front of the one that was removed. Finally, we can decrease the size of the list by 1 and then return the removed element. So that's actually all of the methods except for the iterator method for our S-linked list class. To implement the iterator, we need to create a iterator class. Now remember that an iterator sits between elements. So that red arrow is the iterator that's between the third and the fourth element of this list, right? So index 2 and 3. Now this iterator is in the middle of the list. So we know that the previous call to next returned the element C, right? So the element returned by the most recent call to next is in the node that's immediately in front of the iterator. We're going to use the field previous to refer to the element returned by the most recent call to next. We're also going to keep a second field called previous, which is the node that's in front of previous. Now the reason we want previous is because when we implement the iterator's remove method, we need to remove that node. Right? Now remember, to remove that node from a linked list, we need the node in front of it. So it's useful to keep track of that node using this variable previous. So this slide just repeats what I just said. Previous is the node that's going to be removed when we call the iterator's remove method, and we need previous to actually remove that node. Our iterator method simply returns a new LL iterator. So LL iterator is the name of our linked list iterator class. Like the array-based list, the iterator for a linked list is a private inner class. So our LL iterator class implements the iterator interface. Its implementation, we have two references, right? So there's a reference to the node previous, and there's a reference to the node previous. The constructor for the iterator sets previous to null, and it sets previous to this funny new node. So let's explain what this line here is doing. So at the start of an iteration, there is no node for previous to refer to. Right? So here's our iterator. There's no node previous or previous. And so if we were to implement the iterator this way, then we'd have to set previous equal to null. Unfortunately, that introduces some special cases, and I'd like to avoid having those special cases. So one way we can do that is to enforce the iterator class invariant that the previous node never be null. Now you might wonder, how can the previous node never be null? There's no node here, right? And so the trick is the iterator constructor can insert a node in front of the head node. And that node only has one purpose. That purpose is to assure that previous is never null. Right? So the constructor can make a new node. There's no element stored in the node. Right? And it can make that node, it can link that node to the actual head node of the linked list. Now the linked list doesn't know that this node exists. The iterator knows that this node exists, but the linked list class itself does not know that node exists. So that node there, whose only purpose is to ensure that there's always a node in front of the head node, is called a sentinel node. So in our constructor here, right, when we make that sentinel node, it stores no element, and its next link points to the head node of the linked list. Now remember that LL iterator is an inner class. So it has access to the fields of the S linked list class. And also remember that the way you get access to those fields is to write the name of the class, followed by .this, followed by the name of the field. The hasNext method returns true if there are more elements to visit. Right? So how do we know if there's more elements to visit? Well, if previous.next is not null, then there's more elements to visit, right? So there's another node after previous, right? At the end of the iteration, right, where the iterator is at, it has visited all the elements, right? Then previous.next is null. Right? So implementing hasNext is trivial. You simply return this previous.next is not equal to null. Next advances the iterator one position in the list, and it returns the element that it steps over. So if we have an iterator here and we call next, it's going to move the iterator one position to the right, and it's going to return the C in this case. Now when we advance the iterator, we need to advance previous, previous, and previous, right? So they both move one position to the right. So the next method, the first thing you do is you check, is there actually a next element? If there isn't, we throw an exception, right? Otherwise, we're going to set previous previous to this previous, right? And then we're going to set this previous to this previous.next. Right? What's the element that we're going to return? Well, we want to return the element that's sitting in the updated value of previous. Right? So we want to return the C in this case. So the last thing we do is return this previous.elem. This line here, this previous equals this previous equals this previous. What you must not do here is write this previous equals this previous dot next, and you'll see why when we implement the remove method. So to remove an element, except for the element in the head node, we can remove the element using our remove after method. So the element to be removed in this situation here is the element that's, or is the node that's referred to by previous. Right? To remove that element, we just call remove after, using previous as the node. Right? So we want to remove the node that's after previous. After removing the node previous, we get the list that's shown below. So if we have our iterator, here's previous. There is no node previous anymore because we removed it. In our iterator implementation, previous should always refer to the node that's immediately in front of the iterator. So in other words, I want previous to refer to that node there. And we can do that by setting previous to equal previous. And now the question is what do we do with previous? So it turns out we're going to set previous to null. The reason why we're going to do that is because when previous is null, we're going to use that as an indication that remove has been called. And remember that you're only allowed to recall remove once every time you call next. Right? So after removing the node, we're going to update previous, so it points at the old previous. We're going to set previous to null. Right? Now we know by looking at previous that we've called remove once for a single call to next, and we cannot call remove again without calling next again. So previous equal to null is our indicator that remove has already been called for the most recent call to next. What about removing the first element in the list? So if we want to remove the first element in the list using the iterator, then we have to call next once on exactly once. And that moves the iterator to the position shown here. So calling remove on the iterator will remove that node there. Now to remove that node, we're going to use the remove front method. Now remove front adjusts the head node of the list so that it points to the element after the iterator. Uh, the Now the problem is our iterator still has a reference to that old head node, right? So previous still refers to that node A. Previous still refers to the sentinel node. We're going to set the element that's in the node previous to null. So we're going to convert the old head node to a sentinel node, right? So now we've got an iterator where the previous node now refers to a sentinel node. So it's not. So we don't have to set previous to be equal to null. And then we update previous so that it's null. That indicates that remove has been called for the most recent call to next. The implementation of the remove method looks as follows. Right. So the first thing we do is we check is previous null. If it is, then we've either called remove once already for the most recent call to next, or the iterator hasn't moved from the front of the list yet. So in other words, there is no element that's been returned by next to remove. Next, we're going to check if the previous node is equal to the head node of the list. And if it is, we're going to call the remove front method to remove that head node. We're then going to convert the old head node to a sentinel node by setting the element to null. Right? Now remember, the old head node is pointed at by this previous. Finally, if we're not removing the head node, then we're going to call remove after. We're going to pass in previous as the node to remove, as the node that's in front of the one that we want to remove. We're going to set this previous to this previous. We're going to set previous to null. And that completes the implementation of the iterator class. The exam for CMPE212 is on the 24th of April between 7 and 10 p.m. For CISC124, it's on the 28th of April between 2 and 5 p.m. The exams are different slightly for the two courses. Both exams are online on OnQ. You'll see them appear under quizzes on OnQ, probably the day before the exam. The exams are unproctored. The expectation is that you are working alone on your exams. The topics covered by the exams are described on the slide here. So as the course progresses, topics build on topics from earlier in the course. So what does that mean? That means you need to be familiar with all of the course material. However, there are no questions specifically related to the material tested on the midterm. Right? So in other words, there are no questions on basic Java, right? How to write a loop or how to write an if statement or make variables or things like that. Similarly, there's no questions specifically aimed at using strings or lists. So most of the topics focus primarily starting from part 2 of the notebooks. Right? So in other words, creating classes, relationships between classes, so that's aggregation, composition, inheritance. And then the fourth part of the course, which is generics and data structures. There is no need to memorize the details of a class's API. For example, you will not be asked what the method XYZ does in the class ABC. Right? You can always look it up. Right? You can always search the Java library APIs and find out what the method does. You do need, or you are expected to know the basic functionality of the fundamental Java classes that we used in the course, right? So you're expected to know the basic methods of string, list, set, and map, for example. You do have to write code on the exam. But if you find yourself writing a lot of code for any given method, then you should probably reconsider your answer. So the design of the exam is such that no method is more than, I don't know, say 10 or a dozen lines of code. You do not need to provide JavaDoc unless you are explicitly asked for it. So don't waste time writing JavaDoc because it takes a lot of time and you won't be getting any marks for it anyway. To study for the exam, it would be useful to review the assignments and their solutions. Of course, it's useful to review the lecture slides and the notebooks and the notebook exercises.